Hi. Today we're going to look at a Dirichlet series, and we're going to try to compute it using Euler Product. So let's refresh our memory here. Let f of a equals the sum as n goes from 1 to infinity of m of n over n to the a. This is an example of a Dirichlet series. And here, m is a multiplicative function, i.e., m of a times m of b equals m of a times b, if the greatest common divisor of a, b is 1. In other words, if they're coprime. And under certain conditions on m and a as far as convergence, f of a will be equal to the Euler product, in other words, the product of all primes, of the sum as e goes from 0 to infinity of m of p to the e divided by p to the e to the a. So today, just let's look at an easy example of this. So in our case, we're going to let m of n equal tau of n, where tau of n equals the number of divisors of n. Well, tau is a multiplicative function, as you can check out. So let's let p be prime, any prime. The divisors of p to the e are, of course, 1, p squared, ... all the way up to p to the e. So therefore, tau of p to the e must equal e plus 1. We have a 1, and then from p to the e is another e of them. So in total, there are e plus 1 divisors. Okay, let's set this as our Dirichlet series. So the sum as e goes from 0 to infinity of tau of p to the e over p to the e to the a, just simplifying, equals the sum as e goes from 0 to infinity of e plus 1 over p to the a to the e. And this equals the sum as e goes from 0 to infinity of e p to the minus ae plus the sum as e goes from 0 to infinity of p to the minus ae, just separating these two terms. And we can do that because both these series are convergent, since p to the minus a is less than 1. Well, this equals p to the minus a times the sum as e goes from 1 to infinity of e times p to the minus a all to the e minus 1. Notice I pulled out a p to the minus a out front, and then of course I had to counteract that with the p to the minus a to the minus 1 on the inside. And then plus the second term, the sum as e goes from 0 to infinity of p to the minus a to the e. And this equals p to the minus a times the derivative with respect to x of the sum as e goes from 1 to infinity of x to the e, where x will be p to the minus a. Then plus the second term again, the sum as e goes from 0 to infinity of p to the minus a all to the e. Now simplifying, this equals p to the minus a times the derivative of x over 1 minus x at x equals p to the minus a, plus our second term, 1 over 1 minus p to the minus a, simply a geometric series in the second term. And this equals p to the minus a times the quantity 1 over 1 minus x plus x over 1 minus x quantity squared at x equals p to the minus a plus 1 over 1 minus p to the minus a. Okay, we're almost home now. This equals p to the minus a times 1 over the quantity 1 minus p to the minus a squared. When we insert p to the minus a for x, plus our second term again, 1 over 1 minus p to the minus a. Bringing these together equals 1 over 1 minus p to the minus a quantity squared. This implies our Euler product is the product over all primes of 1 over the quantity 1 minus p to the minus a squared. And we can separate this into two terms since it's a product. This equals the product over all primes of 1 over 1 minus p to the minus a times the product of 1 over 1 minus p to the minus a. Well, each one of these is a famous quantity. Each one of these equals zeta of a. So finally we get zeta of a squared. So our Dirichlet series in this case equals zeta of a squared. And we were lucky this time. We were able to convert our Dirichlet series into some function involving zeta quantities. We can't normally do that, but in this case we were able to. And this ends the video. Thank you very much for watching.